So really, when it boils down to it, all implicit differentiation is, mathematically, is an application of the chain rule. When you differentiate something with respect to x, if you happen to bump into something which is not x but a different variable like y, you simply apply the rules for differentiating, whether it's the power rule or other rules we'll encounter later, but then you follow it up with the chain rule, which says we have to multiply by the derivative of what you wrapped the exponent around. And if you're wrapping the exponent around y, then that means you have to multiply by dy dx. So anytime you differentiate something that has a y in it, you have to follow it up by multiplying by dy dx whenever you apply a rule. That's all it boils down to mathematically. What it boils down to for a reason why this is important is when you take a look at, we can pick many different examples, but if you were to take a look at this example or this example or this example, you cannot easily rearrange for y. Sometimes it's possible to rearrange for y by being clever, but what you end up creating a lot of the time is y equals plus or minus an expression. And that means that you don't really get one function for y, you get multiple functions, and that would mean differentiating multiple functions. Sometimes you can rearrange for y. I wouldn't recommend it, but it is possible to rearrange, for example, this function for y. It's going to be 6 minus x squared raised to the third. And because you're going to take the square root to get y, there's no plus or minus involved. But anyway, bottom line is I wouldn't rearrange too much. Okay? Does anybody have any questions you would like me to go over? Go ahead, Marcel.
Can you do 2C?
2C, certainly. There is a, kind of a light at the end of the rainbow in some of these questions, much like question number 1 on your assignment that's due Friday. And that's that you don't necessarily have to simplify everything to get an answer. Let me show you what I mean. When we differentiate this, I want to rewrite it so it's a little bit bigger for me. I'm going to think of the x cubed y squared as being a product of x cubed and y squared. So now I'm ready to go. Make sure I wrote it down correctly. Looks good. So when I differentiate x squared, I get 2x. When I differentiate x cubed y squared, I'm differentiating a product. So when I say plus, everything that I write after that, until I get to the y cubed, everything that I write after that is the derivative of x cubed y squared, which is found using the product rule. And the product rule is going to have a plus in it. It's going to be the derivative of the first times the second plus the first times the derivative of the second. And because I'm adding that, I don't feel the need to put a set of brackets around that whole thing. If I were subtracting because maybe it was a quotient law, then I would do that. So the derivative of the first, I'm looking at this as being the first, would be 3x squared times the second, which is y squared, plus the first, which is x cubed, multiplied by the derivative of the second, which is 2y to the 1, dy dx. Again, to really break it down, and I'm not going to be doing this all of the time, but if you want to differentiate with respect to x, this thing, it's a power, which means you're going to take the exponent of the power, which is 2, move it in front of the base, which stays the same, drop 1 from the exponent, but then you have to multiply by the derivative of what you wrap the power around. That's why we learned the chain rule first, so we could understand implicit differentiation. So multiplying by the derivative of what we wrap the power around, we wrap the power around y, so that's why the derivative of y squared is 2y dy dx. We're okay to that stage? Okay, and then we have minus y cubed in the original relation, so we have to subtract the derivative of y cubed, which is 3y squared, dy dx, for the same reason that we got 2y dy dx for the derivative of y squared. Now, I just noticed you erasing something. Does that mean you figured out what happened? Okay. I'm going to continue anyway. We're so close to being done. Equals the derivative of 13. Well, 13 is a constant, so that's 0. Now, I mean, above all things, we're here to learn math. We're here to learn to be better at math. So I could just jump into how to get the answer, but as a side note, what you would want to do now is move all of your what we would want to do now is move all of the terms that have dy dx to one side of the equation and all of the terms that don't to the other side. We would want to minimize the number of negatives, and I think in this particular case I would move the dy dx terms to the right-hand side. You might notice that with this term here, I've played around with the order of things, and I've, instead of writing x cubed times 2y, I wrote 2x cubed y. This is equal to 2x plus 3x squared y squared. So you would now, on the right-hand side, if you wanted to get an expression for dy dx, and we don't need to do this in this question. I'm going to come back to that in a bit. You would factor the dy dx out, leaving you with dy dx times 3y squared minus 2x cubed y. And for work that is as involved as what we're doing, I should chastise myself for not actually double checking any of the steps. I never did. I wrote it down correctly. 2x, 3x squared y squared plus x cubed 2y dy dx minus 3. This line is okay. I moved those two terms over. I think it's all fine. But I never personally checked. So that would mean dy dx is equal to the 2x plus 3x squared y squared over this thing. We have to divide by that, which is 3y squared minus 2x cubed y. And the question was, what is the slope of the tangent at the point 1 comma negative 2? So that means that we have to put in, I remembered that correctly, right? 1 negative 2? We have to put in for x 1 and for y negative 2. So what are we going to get? 2 times 1 plus 3 times 1 squared times negative 2 squared over 3 times negative 2 squared minus 2 times 1 cubed times negative 2. Better double check all of that. The negative 1 goes with the x. The 1 goes with the x. The negative 2 goes with the y. It's a lot of numbers, and sometimes you just get frustrated. You have to check all of these things, but I believe it's okay. On the top, I'm getting 14. Negative 2 quantity squared is 4, times 3 is 12, times the 1 squared is still 12, plus 2 is 14. On the bottom, I have 12 plus 4. I believe on the bottom I have 16, but maybe you can help me out and double check the bottom. Pretty sure it's 16. Negative 2 squared is 4, times 3 is 12. 2 times negative 2 times 1 is negative 4, and I'm subtracting negative 4. 12 minus negative 4 is 16. So this works out to 7/8 is the answer. we didn't have to do it this way. I mean, you had to find the derivative. What you could have done, and I'm not going to, so we're okay with this question now, I think. I'm not going to do all of the work on the board, but what we could have done is at this point put in the x and the y numbers. And when I put x equals 1 in, I get 2. I get 2 plus when I put 1 in for x here and negative 2 for y, I get 12. 3 times 4. Here, when I put 1 in, this becomes 1. When I put negative 2 in, I get negative 4 dy dx. Over here, I put negative 2 in and I get minus 12 dy dx. Negative 4 dy dx and negative 12 dy dx is negative 16 dy dx. And if you move it over, you have 16 times dy dx. You're going to have to take this 14 that's over here and divide by that 16. It's kind of like what I told Mackay. We were talking about the assignment, question 1, where you have to find the slope of the tangent line to find the equation of the tangent in that assignment. You don't have to simplify the derivative. You can just find the derivative in unorganized, unfactored, unsimplified form and then put in the value of x and find the slope. Anyway, is that okay, Marcel? Okay. Any other questions anybody would like me to go over? 1C? All right, Demi. We have xy equals 4. And I just want to check, Demi, this is the question you're asking about? Perfect. So if we use implicit differentiation to do this, and by the way, everybody, Demi and everybody, this is a case that you could rearrange for y. There is absolutely no reason why you couldn't rearrange this for y and differentiate the result. But I'm going to use implicit differentiation, and in order to make it work, I have to remember that xy is a product. So the derivative of the first is 1 times the second. Just to be clear here, this is the first, this is the second. So the derivative of the first is the derivative of x, which is 1, times the second is y, plus the first, which is x, times the derivative of the second, which is dy dx, and this is equal to the derivative of 4, which is 0. So is that line okay, Demi? Perfect. So now I have to rearrange for dy dx. I'm going to choose to just subtract y from both sides. So on the left-hand side, I have x dy dx. And I'm going to subtract this y to the other side, making x dy dx equal to negative y. And you end up with dy dx equals negative y divided by x, because I have to divide by this x. Now, I don't know, maybe you can help me out or somebody here can help me out. Is that the answer in the back? Because it may not be the answer in the back. The answer in the back may be negative 4 over x squared. And that's what it is. So this is why you're asking, I think, this is why most people would ask about this question, is you do this and you get y over x, and then you go in the back and it says that you have dy dx is negative 4 over x squared. Well, there's two ways to explain. There are two ways to explain why the derivative is that. One of the ways is to go back to the original relation, which is xy equals 4, and to write it as y equals 4 over x. And if we've determined that dy dx is negative y over x, then we've determined it's negative 4 over x over x. So what I've done here is I've taken this and I've put it in here. Well, I've put it in for the y, so I have negative of that. And if I take a look at this as a rational expression, I can multiply the numerator and denominator by x and get negative 4 over x squared. So Demi, is that okay? Okay. One other comment. I started off when I looked at this and said, this is one that you could certainly rearrange for y. If you scrap all this and you go, well, if xy equals 4, then y equals 4 over x. After all, ultimately, probably the most important reason why you would ever use implicit differentiation is it's easier, because it's difficult to rearrange for y. But this is very easy to rearrange for y. We can see that y is 4x to the negative 1. This is pre-differentiation. That's the function. And it is a function. It's not just a relation that's not a function. And that means I can use the power rule. The derivative of y is dy dx. The derivative of 4 times x to the negative 1 is negative 4 times x to the negative 2, which, that's a lot simpler and easier than using implicit differentiation. Other questions? Liam? 6? Certainly. So this curve, it's the infinity shape, is called the lemniscate, and we want to find y prime. And I don't know, it's been a while since I've done this one. I don't know what level of simplification we're going to pursue. It may be very little, because ultimately you're going to use the derivative to find the slope of the tangent at negative 3, 1. But let's dive in. And given the nature of one of the problems we're doing today, this is really good as a warm-up, to warm up our math skills. Okay? So let me rewrite this. I have 2 times x squared plus y squared quantity squared equals 25 times x squared minus y squared. I suppose you could take on the left-hand side x squared plus y squared times x squared plus y squared and start walking down that path, but I think that's going to create problems later on. So when I look, Liam and everybody, at the left-hand side, it is a power. It is 2 times a base raised to an exponent. So I'm going to apply the power rule by wrapping this exponent of 2 down in front, multiplying by the coefficient of 2. The base is rewritten exactly the way it is, and I drop 1 from the exponent, and then I multiply by the derivative of what's inside. Now, earlier on, we added the derivative of a product, and I made a big deal that the derivative of a product is going to have something plus something. But I said, since we're adding it, I don't need brackets. Well, we're finding now, we have to multiply now by the derivative of what's inside. And what's inside is a sum. So we have to multiply by a sum. But that means that set of brackets is important. It means that both parts of the sum are multiplied by that thing in front. Left myself way too much room, but that's okay. What is the derivative now of x squared? It's 2x. Plus, what is the derivative of y squared? It's 2y dy dx. So let me run through this again without interruption. I wrap the 2 down in front, and it becomes 4 times the same base, which is x squared plus y squared raised to 1 less exponent. Then I multiply by the derivative of what I wrapped that exponent around, which was x squared plus y squared. The derivative of x squared is 2x. The derivative of y squared is 2y dy dx. Are you okay with that on the left-hand side differentiation, Liam? Okay. Equals. Now, this can get kind of sneaky. On the left-hand side, I said, you don't want to walk down that path of expanding it. But I would be tempted in my head for the right-hand side to just think of it as 25x squared minus 25y squared. If I don't, then I have to use the very seldom used derivative of a constant times a function rule, which says the derivative of a constant, like 25, times a function, like x squared minus y squared, is 25 times the derivative of x squared minus y squared. I'm gonna go down this path that I have in green, though. I think it's more straightforward. So I have to differentiate 25x squared, which gives you 50x, minus I have to differentiate the 25y squared, which gives you 50y dy dx. Now, Liam, I don't want to bring up a specific example because I will lose people. I want to just talk in general about logarithms. Sometimes when we solved logarithmic equations for a variable, you ended up, after moving an exponent down in front, having a product of two things where what you were trying to find was buried inside of a sum. And the only way, whether you've taken 30-1 yet or not, the only way to expose that dy dx where we can work with it is to multiply this into this binomial. Once we do that, then we can worry about moving the dy dx's to one side and the non-dy dx's to the other side. So when I multiply the 2x by the 4 and the x squared plus y squared, I get 8x times x squared plus y squared. And then plus, I'm going to multiply the 2y dy dx times the 4 and the x squared plus y squared. So 2 times the 4 gives us 8. I have a y. I have a dy dx. Close brackets there. I have a dy dx, excuse me. And I have a x squared plus y squared. And I'm going to double check all of that. My first product is going to be 8x with an x squared plus y squared, and that's fine. My second product has a 2 times a 4 times a y, which gives me 8y. It also has a dy dx and that x squared plus y squared. Now don't get sucked into factoring anything just yet, because then you're just going backwards. Right? We don't want to factor until we get our dy dx's collected together. This is equal to 50x minus 50y dy dx. So I'm going to identify the terms now that have dy dx in them, and I'll underline them. There's a lot going on in this question. So let me underline the dy dx terms with blue. So those are the two terms that I need to put on the same side. I'm going to choose to move them to the left side. It's not necessarily a matter of minimizing the negatives as it is if I move the dy dx's to the right, they're both negative. I don't want to deal with two negatives. I guess I am minimizing the dy dx's anyway, or the negatives rather. So I have 8y dy dx times x squared plus y squared. I'm going to add this second blue term to the left side to get rid of it on the right. And then I'm going to have on the right-hand side my 50x minus the 8x x squared plus y squared. And I'm going to step back and take a look at it. I think it's fine. But again, 32 i's are better than 2. Look okay, you guys? And I know that's always a difficult question to answer because we've all made mistakes, and you look at your work and you go, well, it looked right. It's a careful consideration of your work that you need to occasionally perform. Now I can take the dy dx out of both sides here, Liam. Dy dx. What will I have left? Man, I'm going to have my 8y. I'm going to have the x squared plus y squared. I'm going to have then plus my 50y. And this will be equal to 50x minus 8x times x squared plus y squared. Double check everything. I took out the dy dx. That looks okay on the left. I'm left with 50x minus the 8x times x squared plus y squared. I can see, by the way, here, there's going to be some level of simplification that's going to happen. Because now I'm going to divide the 50x minus the 8x times x squared plus y squared. I'm going to divide this beast on the left by this beast, or sorry, the beast on the right by the beast on the left. So this is going to be over 8 times y times x squared plus y squared plus 50 times y. And the reason I know that there's some level of simplification that can happen is I can take a 2 out of the top and a 2 out of the bottom and cancel. All of the coefficients of the terms on the top and the bottom are even. So if I do that, I'm tempted to just do some canceling, but I've always told you I don't like that. So if I do that, I'm going to factor out a 2 and be left with 25x minus 4y x squared plus y squared over, I'm going to factor out a 2 from the denominator as well and have 4y x squared plus y squared plus 25y looks good. If I cancel those 2's, that's my derivative. And there's really nothing else you can do here. If you're wondering about the brackets on the top and the bottom, I really ought to have another bracket ending that starting bracket. But once we cancel the 2's, you can get rid of those green brackets. There's, could you, there is one mistake there, isn't there? Has anybody caught it? See, it's like finding a golf ball in the woods. After you've even seen where it lands, it's like, where is it? This y on the top by the 4 should be an x. Okay. I had noticed earlier that both of my terms on the top had x in them and both of my terms on the bottom had y. So is there anything else you could do here? Could you factor the top? Sure, you could take an x out of the top. You could take a y out of the bottom. But to what end? What would be the reason, the motivation for doing that? And I would say there isn't one. So I'm going to end it there. If you want to do b, which is, I believe, to find the slope of the tangent at what I think was negative 3, 1, then you're going to have to put negative 3 in for x, positive 1 in for y, and very carefully do some calculations. Okay. I am going to end the questioning there for today for now because we do have one more lesson. Keep in mind we have at least 3 days of review. Starting tomorrow, we have Friday, and we have Monday. So if you do have further questions that I didn't get to today, please write them down or make a note of them, and we will find time to go over them. Okay. So we are looking now at what are called higher order derivatives. And this, in principle, the concept of a higher order derivative is not a difficult one. It turns out that there's a second derivative to a function, and there's a third derivative to a function, and there's a fourth derivative. And I guess theoretically, in principle, there's no end to this process. If I said to you, if I give you some kind of expression and I wanted to keep you busy for a week, I'd say find the 100th derivative. Okay? It's just going to mean a lot of work. I would never expect you to find the 100th derivative. Okay? There's an exception to that we will get to today, actually. And we're going to continue to correctly interpret derivatives. The only problem is we do understand right now in this class what the first derivative means. The first derivative is a means for you to find the slope of a tangent. You don't know what the second derivative means or what the third derivative means. And I'll tell you right now, the further you get away from the first derivative, the less meaningful the derivative is. So the second derivative definitely has a meaning. The third derivative has a meaning, but it's a little more greasy to wrap your head around and get a good hold on. The fourth derivative is almost impossible for most people to understand what it truly means about the function. Once you get to the fifth derivative, forget it. So, some definitions. The second derivative of a function is the derivative of the function. Like, let that sink in, and I'm already starting to see some of you nod. I didn't accidentally repeat words there. The second derivative of a function is what you get is if you differentiate the derivative of the function. In other words, if you take the function and you differentiate it, you'll get the derivative, and if you take the derivative and differentiate it, you get the second derivative. To find the second derivative, you look at the function, you differentiate it once, whatever you get, you differentiate a second time. And that second derivative, which is the derivative of the first derivative, that second derivative is the second derivative of the function. If I said to you, find the third derivative, then you would continue. So that's why I'm saying in principle, this is not too difficult. If I say, what's the third derivative of a function, that just means you have to differentiate 3 times. And you can find the fourth derivative this way, or the fifth derivative, or as I said, in principle, any higher order derivative. These are called higher order derivatives. Now we have some notation, and I know this is all filled in your handout, but I want you to focus up here. One of the ways you can describe a function is to say y. And I think y, although function notation is very valuable, I think for differentiation, just the variable is the better way to go, y. So if you want to write out using, I believe, that's not Leibniz's notation. It might be Leibniz's notation. It doesn't matter. If you want to use the prime notation, then the first derivative is designated as y prime. And by the way, if you use the function notation, you can say the first derivative is f prime of x. All right, that's nothing new. The second derivative, which is the derivative of the first derivative using the prime notation, is y double prime. That's the second derivative. And if you use the function notation, it's f double prime. And this continues into the third. The prime notation is really awkward, and for that reason, we don't use any notation for the fourth derivative of a function that is similar to any of these. We don't write y quadruple prime. We just don't use that notation. But we do use, and it grinds my gears that we do this, we do use that kind of notation for function notation for the fourth derivative. And I absolutely hate this, because in mathematics, that is treated as an exponent. For example, you should know from Math 30-1 that if you have something like sine to the 4 of x, that does not mean the fourth derivative of sine of x. It means sine of x raised to an exponent of 4. So, although this is correct, I don't even know how to pronounce this other than to say the fourth derivative of f of x. Although it's allowed, I will never use that. I will always use the notation that's in the bottom row of your chart, which I will explain in a second. And by the way, in general, then you can say using this middle notation that the nth derivative, 7th, 10th, whatever, could be designated with that notation. I like the, I know I'm getting my names mixed up. I like the dy dx notation. I'm not going to say who invented that notation, because I think I've got them scrambled up in my head. Unfortunately, the second derivative takes on a little bit of a twist, and you don't really learn in this course. We might talk about it later, why it's written this way and why it's pronounced the way I'm going to pronounce it, which is this. It seems, unless you understand a deeper meaning, that this is really wrong. That's pronounced d2y dx squared. So we pronounce the 2 on the bottom as if it were an exponent, and we pronounce the 2 on the top as if it were just a number. So it's d2y dx squared. That's the second derivative of y with respect to x. The third derivative is d3y dx cubed. There's a reason why. That bottom number actually is an exponent in terms of calculus, but to explain it here is not necessary. It's confusing. The fourth derivative would be d4y dx to the 4. The nth derivative would be dny dx to the 4. So we just have to get used to that notation. I'm going to prefer to use that bottom set of symbols and notation groups for second, third, fourth derivatives, etc. So does anybody have any questions? One, about how you find, say, the fifth derivative of something. You'd have to differentiate the fourth derivative. But then you'd have to differentiate the third before you got to the fourth. Go ahead.
Just thinking about more simple derivatives, eventually won't they just become zero?
Some. So I had said, what Evan is asking is, if you continue this process, wouldn't it eventually become zero? And some will. When I said to you, I would never expect you to find the 100th derivative, it's a bit of a lie. Because, and can you hang on to your question? Does anybody have any other questions with this so far? Go ahead. Be able to combine what? Yes. If you're asking, this has nothing to do with slopes of tangents. If you're asking, do we have to apply all of the rules that we've been learning and implicit differentiation included with higher order derivatives, the answer is yes, because this is a question we're going to do. Okay, and just to show you, this is from, I don't know if it was last semester, this is how much work is going to be involved to do this question. And okay, so this is not an exam question, Liam. This is not an assignment question. This is a learning, getting better and better at math and algebra and calculus question. But yes, we have to combine them. Other than Evan's question, which we're going to answer by doing question 1, does anybody have any other questions about higher order derivatives so far? Evan's question is, if you keep doing this, won't it eventually become 0? And the answer is, if the original function is a polynomial function, yes. So I think with a little bit of thought, I think everybody should know that the 100th derivative of this will be 0. Because when you differentiate a polynomial function, the degree of the polynomial function drops by 1 each time you differentiate. So let's do this. What are the first 4 derivatives? This is not a gargantuan problem for us to solve. The first derivative, which would be dy dx, is going to be 20. I had to retype this lesson because some of my files were corrupted in Google Drive. Can you check to make sure that's the same function that's in your notes? It is. Okay. Thank you. It will be 20x to the 4 minus 15x squared plus 1. Now be careful, because differentiating this is so simple, you might just put yourself to sleep and make a mistake, right? I mean, it's almost boring. I swing the exponent down, drop 1 from the exponent. So I think we're okay with that derivative. I differentiate it again. So what I'm finding now is the second derivative, d2y dx squared. And it's going to be 80x cubed minus 30x plus 0. And by the way, there are real important applications with the second derivative. When we get into the next unit and we deal with graphing functions, any functions, the second derivative is crucial in understanding the shapes of the graphs in particular areas. Double check my work, it looks fine. The third derivative, d3y dx cubed. I'm sorry, I didn't check with you. Second derivative looks okay, I hope. Okay. Third derivative will be 3 times 80, which is 240, x squared minus 30. So we're just differentiating polynomial terms. The fourth derivative, which I'll just put over here so we can see all of them together, will be, you know what? I'm going to change my mind and put it below. I'm teaching a bad habit here. As soon as I wrote it here, we're taught, and you should be working down. As soon as I wrote it on the right, I immediately looked above to find out what to differentiate. And I realized that it wasn't above, it was to the left. So I differentiate again, that's 480. X, 480x. How's my arithmetic there? Good. So any questions with finding the fourth derivative? The fifth derivative would be 480. The sixth would be 0. The seventh would be 0 because anytime you differentiate a constant, you get 0. So I've answered your question, I think. Right. However, if I say to you, find the second derivative of this, and do me a favor and check again to make sure I've retyped this function the same as what's in your handout. Okay. It's not necessarily going to get simpler. It may, by a fluke of the numbers, get simpler, but in order for us to differentiate this once, we have to apply the quotient rule. So the derivative of the top multiplied by the bottom minus the top times the derivative of the bottom over the bottom squared. I'm going to double check my work, and you should double check my work and your work as well. But it looks okay to me, except for the fact that I forgot to write squared. By the way, when I talked about number 3 and I said this is not an exam question, this is a basic question. For us to graph functions, you have to be able to find the second derivative of this. And it's going to be interesting when we get to that stage in the course, because one function that we have to graph might take us an hour, because you have to find the first derivative, you have to find the second derivative, you have to do what's called a first derivative chart, a second derivative chart. You have to do all these things. So it's not a quick, simple process. So I want to simplify this first derivative as much as possible before I differentiate it again, which I think that makes sense, doesn't it? You don't want to differentiate something that's complicated. So how do we simplify? We factor dy dx. Let's see, I can factor out an x and a 2. I'm factoring out of this term and this term. So what do I have left? Out of the first term, I have a 2 and then an x squared plus 2. Minus, out of the second term, I have a 2x squared minus 5. This is still the first derivative. Let me double check by expanding that in. So what's going on in my head right now is I'm doing this to make sure I get what I started off with in the line above it. 4x times x squared plus 2 minus 2x times 2x squared minus 5. It's okay. So now I simplify what's in the brackets, and as is almost always the case, it cleans up a lot. We have 2x squared minus 2x squared. It's a wash. There's nothing left for the x squareds. Then we have 2 times 2, which is 4, minus negative 5. So we end up with, I really am not normally a big fan of doing this, and I wouldn't recommend it on paper when you're working, but this is 9, right? I mean, we could rewrite the whole thing. This is not a bad strategy, by the way. Just make sure you're right before you go on. So then if I take that 9 times the 2x, what I have for the first derivative is 18x over x squared plus 2 quantity squared, which isn't bad. That's not a bad first derivative. Not that derivatives can be bad, but you know what I mean. It's not like some kind of wild expression. Now I'm ready to differentiate again. So when I differentiate the left-hand side, I'm finding the derivative of the derivative, which is the second derivative of y with respect to x. And this is a quotient again. There's a top and there's a bottom. So the derivative of the top is 18 times the bottom, which is x squared plus 2 quantity squared, minus the top, which is 18x, times the derivative of the bottom. Okay, well, the bottom is a power. So I'm going to take that 2 and wrap it around. I'm looking here. I want to be very careful here. I'm looking here and differentiating that. I'm going to wrap that 2 around the x squared plus 2, reducing the exponent by 1. This is why I don't want you to use prime notation. And then I'm going to multiply by the derivative of what's inside. So let's check this all together. Looking at the words above, top and bottom, 18 is the derivative of the top, times the bottom, which is x squared plus 2 quantity squared. The quotient rule says we have to subtract. The top is 18x. This whole thing is the derivative of the bottom because we wrap the 2 around the x squared plus 1, drop. I understand what the wrinkle in your forehead is. We wrap the 2 around the x squared plus 2. That's what you were trying to communicate to me. Good. I knew I wrote something wrong when I start to see those wrinkles. I wrap the 2 around the x squared plus 2 and drop 1 from the exponent, and then I multiply by the derivative of what's inside. This is now over the bottom squared, which means it's now going to be over x squared plus 2 to the 4. And we're back kind of in the same boat that we were in before with the first derivative. We've got 2 terms on the top. Let's factor. So what I am looking at on the top is this term minus this term. So what do they have in common? Well, there's an 18 in each, and they both contain x squared plus 2's. There's an x squared plus 2 squared in the first term and raised to the 1 in the second. So we've learned that you take out the base that appears in both raised to the lowest exponent. And in the first term, that base is raised to the 2, and in the second term, it's only raised to the 1, so you're going to take it out raised to the 1. What do we have left? Out of the first term, we're going to have x squared plus 2 to the 1, because we took out x squared plus 2 out of x squared plus 2 times x squared plus 2. I don't know, I got that number 1 stuck in my head. We have an x squared plus 2 left, minus, we took out of the second term 18, which means we still have this 2 and this 2, which is 4. We still have this x and this x, which is x squared, and we're just about done. This is over x squared plus 2 raised to the 4. I simplify the leftovers in the brackets in the numerator. In other words, I'm eyeballing this right now, and I have 2 minus 3x squared, because I have 1x squared minus 4x squared, that's negative 3x squared. I have an 18 in the numerator as well, and then this base to the 1 over that base to the 4 will give us that base cubed. It's like having a over a to the 4. You're going to have 1 over a to the 3. That's the second derivative. I probably should write d2y dx squared beside it. Any questions with that? Go ahead. Certainly. Is that far enough there? No. So, of this entire first term, I am taking out the 18 and an x squared plus 2. So I'm taking out the 18, that's going. I'm taking out this, that's gone. So I'm left with, beside the 18, I'm left with the x. Then I'm left with another factor of 2. Later on, after the x squared plus 2, I have another 2 and another x. Does that answer your question? Okay. So the stuff that I have not highlighted on the top right-hand side of the screen is the leftover out of the second term, and it's just 4x squared. All right, so the plan, we have seminar tomorrow, right? So the plan is to use our seminar as time to practice higher order derivatives, as well as, taking your math home tonight. But this is going to take us pretty close to the end of the class. Okay? But again, we have seminar tomorrow, plus we have at least 3 days of review. I want to really point out to you the purpose of this question, first of all, is not because everybody is expected to be able to do it on their own. If you cannot do this on your own, that's pretty typical at this level. The purpose of this is not to scare you. The purpose of this question is to get everybody to be a little bit better at their math skills, following the rules of differentiation, and maybe to give you a leg up on your competitors next year when you're in university. Okay? So we want to find the second derivative. By the way, Liam's question was originally, are we going to have to find second derivatives using implicit differentiation? And I said yes. There are simpler ones that you would be expected to do on your own. Okay, so we're going to differentiate this first. The derivative of, well, I'll rewrite it. We have 3x squared minus 4x times y, and I'm writing it as in that fashion because looking ahead, I'm going to have to find the derivative, and it's a product. Plus 4y squared equals 1. By the way, finding the first derivative is pretty simple. So let's differentiate everything with respect to x. The derivative of 3x squared with respect to x, I better make sure. Did I retype it to match what's in your handout? Okay, I just want to make sure, because like I said, I had to retype this in Notebook. The derivative of 3x squared is 6x, minus the derivative of 4x times y is going to have to be found using the product rule because 4x times y is a product. So the derivative of the first is the derivative of 4x, which is 4, multiplied by the second, which is y, plus the first, which is 4x, multiplied by the derivative of the second. Well, the second is y. The derivative of y is dy dx. Are there other ways you could have handled that without putting minus brackets 4xy? Sure. You could have put plus and thrown the negative on the 4x as part of the first. I like this better, though. I'll finish this whole line, and then we'll double-check the line. Plus the derivative of 4y squared is 8y dy dx equals the derivative of 1, which is 0. So let's all double-check that. Minus would be 4y, 4x dy dx. But I think it's good. So I'm going to peel off the brackets. Because of the amount of work involved in this, I don't want to rush anything here. If I were working on this on my own, I might have peeled off the brackets and done some rearranging in the same step. So all I've done there is I've said, since I'm subtracting 4y plus 4x dy dx, let's subtract both of those terms. I am now going to move my dy dx terms, and you know what? Let's do this first. Take a look at that whole line of math. Is there something we can do to just relieve the pressure a little bit on what we're doing here? Grant? Factor out of 2. And this is interesting because in earlier math courses I would tell people, factor it out and leave it there. Don't divide it because that leads to problems later. But at this level I will tell you, if it's equal to 0, let's do one better than factoring it out. Let's factor it out and divide both sides by 2. If this were equal to y, you're not allowed to do that, right? You can factor it out, but you would have to leave it here. So I'm just going to divide everything by 2, both sides of this equation by 2. And that way we have smaller numbers to deal with in the next step. And I'm going to check because I was writing awfully quickly there. Divided by 2, divided by 2, divided by 2, divided by 2. Looks good. So I'm going to move my dy dx terms to the right side. And write 2x dy dx minus 4y dy dx. You could have moved them to the other side. Doesn't matter. Equals 3x minus 2y. Then, of course, what you have to do is you have to factor out the dy dx on the right so you can divide by whatever's left to get dy dx. And I'm curious, how many of you see what dy dx is going to be? You see those two steps at once. Okay, just again, if you start to skip steps or cut corners, be very careful. Dy dx factored out will leave 2x minus 4y, and this is equal to 3x minus 2y. So we now know what dy dx is. Dy dx is equal to 3x minus 2y over 2x minus 4y. And that, so I just want to stop there. Okay with that step? Okay. That in and of itself is not a complicated derivative. But what you're going to discover here is when we differentiate that whole thing again to get d2y dx squared, we're going to have an expression that contains the first derivative. Let me show you what I mean. Let me rewrite this with the dy dx on the left-hand side and just say dy dx is 3x minus 2y over 2x minus 4y. We need to differentiate this to find the second derivative. And so far, there's nothing that I wouldn't expect all of you to be able to accomplish so far in this question. Getting there, you should know how to do. So I differentiate the left side, which gives me d2y dx squared. And I differentiate the right side, but the right side is a quotient. And you know what? I don't want to totally reverse what I said earlier, but I think most, if not all of you, could do this whole thing on your own if you were very, very careful and methodical. Okay? There's a top and a bottom. So I use the quotient rule. The derivative of the top is 3 minus 2 dy dx. Because the derivative of 3x is 3 and the derivative of 2y is 2 dy dx. Yep.
Would you want to simplify the 2y over negative 4y?
Pardon me? Never mind? You're sure, Liam? Okay. That's the derivative of the top times the bottom minus the top times the derivative of the bottom. This is not done. We still have to go over the bottom squared. and then we're going to double check this entire step. So the derivative of the top is 3 minus 2 dy dx multiplied by, notice I have the derivative of the top in brackets because it's a binomial. I have to multiply that binomial by the bottom, which is a binomial. The bottom is 2x minus 4y, so I'll just indicate where I'm talking. This is the derivative of the top times the bottom. There's my minus in the quotient rule. This is the top, and the derivative of the bottom, well, the derivative of 2x is 2. The derivative of negative 4y is negative 4 dy dx. There's my bottom, and I've remembered to square it. Any questions with that step? Okay. Now, what you need to do here, and it's not difficult, it's just that you haven't done math like this before. You have to FOIL out that stuff on the top. There's nothing common you can take out. I do understand, everybody, that you can take a 2 out of this and a 2 out of that. But I've done a question like this before, and I know that's not necessarily a good idea for learning. Let's leave that 2 in there. We'll deal with those factors later. So I am going to FOIL out this. I'm going to take 3 times 2x, which is 6x. I'm going to take 3 times negative 4y, which is negative 12y. I'm going to take negative 2 dy dx times 2x, which is negative 4x dy dx. And I'm going to take negative 2 dy dx times negative 4y. Negative times negative is positive. 2 times 4 is 8. dy dx times y would be y dy dx. So there's my first outer inner last. I better check that. 6x minus 12y minus 4x dy dx plus 8y dy dx. Okay. Now I'm going to FOIL out the rest, keeping in mind that this is subtraction, and I would rather not rewrite the whole thing twice just because it's subtraction. So when I multiply these two, I get 6x, but I'm subtracting 6x. When I multiply these two, I get negative 12x dy dx, but I'm subtracting that, which makes it positive 12x dy dx. When I multiply my inner, I get negative 4y, but I'm subtracting negative 4y. And my last, I get positive 8 y dy dx, but I'm subtracting it. And I'm going to double check all of those as soon as I make a little bit of room to write my dy dx. I'm just checking here. You guys don't have any problem with space left to write on your paper, right? It's a smartboard thing. So dy dx. Let me get rid of my arrows because they're just visual noise at this point. Double check. I already checked my foiling before. 3x times 2 is 6x, and I subtract 6x. 3x times negative 4 dy dx is negative 12x dy dx, and I'm subtracting a negative, so this becomes positive here, right here. My inner is negative 4y, but I'm subtracting it, so it's 4y, and my last is positive 8y dy dx, but I'm subtracting it. Look good? Okay. Over the bottom squared. Well, let's just make sure here. I'm not going to square it again. The bottom squared is 2x minus 4y squared. I've already squared it. Now we're starting to see some light here. The storm is lifting a little bit because I do have, for example, well, let's go left to right here. I have 6x. Do I have any other x's? I have minus 6x. At this stage of the game, that's what we would call a thing of beauty, right? That's really nice. So we're done with that. Let's do the y's. Oh man, I don't quite get rid of the y's. But I do have negative 12y and positive 4y, which is negative 8y. Okay, well this is getting somewhere. At least we have some terms we can put together. Negative 8y. Well, let's move on. I have some 4x dy dx's. I have negative 4x dy dx's. Oh, I got some x dy dx's here too. I have negative 4 of these, and I have positive 12 of those, which gives me 8 of those. Those are x dy dx's. This is starting to take shape. I have y, oh man, look at that. I have y dy dx's that cancel because I have 8y dy dx's minus 8y dy dx's. And this crossing things out for a marker looking at your work is confusing to me, but for you making sure you don't make mistakes, it's a really good idea. Okay, over, this was supposed to be squared. Looks like most of you caught that. Over 2x minus 4y squared. Now, I have about 10 minutes left, and you're not going to like this next step, but we do not want to write a second derivative in terms of the first derivative. So what we need to do is take a look at what the first derivative is, and I'm going by memory here. I'm pretty sure that's what we got, but you can look up at your work and see that's what you got. And we are going to take this and put it in there. And we're so close. If you knew where this was going, you'd be amazed. We're so close to being done. It looks like the storm is back all of a sudden, but let's continue. d2y dx squared. I have negative 8y plus 8x times this thing, which is 3x minus 2y over 2x minus 4y, and it's over 2x minus 4y. Quantity squared. So all that's happened is we have put in for the dy dx here, we put in dy dx. Unfortunately for us, we've created a complex fraction. We would really like to not have a denominator in the numerator of our derivative, our second derivative. So I'm going to multiply the top and the bottom by 2x minus 4y to get rid of that. And hang on, because I did say I'd go right to the end or close to the end, and it will be. We'll have a couple of minutes left, but I believe the bigger picture here of seeing this math being done and you doing it with me is more valuable than getting this practice problem done for tomorrow or that practice problem done for tomorrow. What happens here? Well, when I multiply this by the negative 8y, I'm left with negative 8y times that thing. When I multiply this 2x minus 4y by this entire second term, the 2x minus 4y cancels. That's why we did it, right? And you're left with the 8x and then 3x minus 2y. And this is over. Now it's over 2x minus 4y cubed. Let's factor out the 8 out of the top. By the way, that's the only thing you can factor out, so it's not really that big of a deal. And we have negative y times 2x minus 4y plus x times 3x minus 2y over, and I'm going to do something with the bottom now. The bottom has 2x minus 4y cubed. That means if I factor a 2 out of the 2x minus 4y, what I have on the bottom is 2 times x minus 2y quantity cubed, which is 8 times x minus 2y cubed, because 2 times 2 times 2 is 8. And the only reason why I'm considering doing that, I hope, is clear, because we had a factor of 8 on the top. Now we have one more step to get what you believe will be the final answer, but is not. And it's to simplify what's inside. So I'm going to multiply the negative y by the 2x. I'm going to multiply the negative y by the negative 4y. I'm going to multiply the x by the 3x. And I'm going to multiply the x by the negative 2y. So I'm going to rewrite the top now as 3x squared minus 4xy plus 4y squared over x minus 2y quantity cubed. And I'm going to pause there. Any questions with that final step? Okay. Now a little bit of a puzzle for you. Oops. Nope. The actual answer to this question is not what we have written. And believe me, it took me a while to come up with one that would work this way. It's actually 1 over x minus 2y cubed. What? Like, how am I able to take this numerator and just write it as the number 1? Does anybody know? I don't want you to tell me the answer. I want to know if you know. Look at the question. The original relation is this. Find the second derivative of 3x squared minus 4xy plus 4y squared equals 1. 3x squared minus 4xy plus 4y squared is 1. I think that's interesting. And again, I'm maybe more interested in mathematical things than you might be. But I think that's amazing that we went through all of this. I mean, look at your work. And I do believe that although not everybody would be able to do this on your own, I do believe everybody involved in this lesson is capable of following the math. You understand the math. It's whether you can put it into practice. So you've grown leaps and bounds in 3.5 weeks. But sometimes you'll see this. Sometimes you get an answer that contains part of the original relation and you can do a sneaky substitution to simplify the result. Let's just put the brakes on and remind ourselves that this entire lesson is not about this example. It's about knowing that if you find the derivative and then differentiate that, you get what's called the second derivative. Differentiate that, you get what's called the third derivative. We are working on this during seminar tomorrow, but just to, give you an idea here, I would say anything in question 1 or 2 are fair game. Like those are basic calculus problems in this course. Liam, in terms of your question, these are all fair game. Some of them might be a little more work, but what makes them easier than the one we did is there's x's and y's. There's no xy terms. Okay? So I thank you for your patience in that very long lesson, but I know it was worth it, whether you believe it or not. Anyway, when the bell rings, have a wonderful rest of the day. Demi, Nicole, and Zach, I don't know what your schedule is for your directed learning, but I would try to find some time either between today and tomorrow's class somewhere where you can practice some of these questions, particularly questions from number 1 or number 2 or number 7. Okay? Have a great day. It's good seeing you guys. And we'll see you tomorrow. See you guys later.